Okay, today we are going to start what is called inference or inferential statistics. Okay, so we've sort of talked about before how sometimes you need to do like a sample survey. There's no way to get the full amount of data, right? It's just not possible due to time and or money constraints. Okay, so we can use inferential statistics, which we will define as using a random sample of data drawn from a population to describe and draw conclusions about that population. Okay, give me a second. Okay, so an example of this would be if like I wanted to know how many pets on average each person in this room had, right? But I don't want to take the time to go around to like 30 people and ask them how many pets do you have, right? I'll just maybe ask 5 or 6 people, and I would say, well, the full class average is hopefully close to the 5 or 6 people that I asked. Okay, so I'm sure you see that there's some risk to this, right? What if I just happen to talk to the only 5 people in this class who don't have pets and everyone else has a pet, but I just happen to talk to those 5 people? It's possible, right? Or maybe I talk to 5 people who all have a lot of pets and most people don't have that many, right? So there's always going to be some uncertainty when you do a sample. Okay, so let's run through another example to try to understand this concept. Okay, so a teacher assigns the students a project. They need to find the average salary of 10 adults who live on their street. Okay, so all 3 of these students live on the same street. So they should all get the same answer because, again, they all live on the same street. So they're all getting the same data. However, none of the students has the time to actually survey all 10 to all 10 adults to get the true answer. So they all do a sample. Okay, so first student Xavier, he talks to 3 adults, David, Frank, and Ingrid, and he collects they're finding the average salary, so like how much money they earn a year. Okay, so because this is not the true mean, it's the mean of a sample, we call this a sample mean. Okay, so the symbol we use for sample mean is X with a flat line over it. So you say this out loud as X bar. Okay, and it looks like an X with a bar on top, right? So hopefully that should be easy to remember. Okay, so we do the mean like always. You add the values together and divide by the amount of values. Okay, so remember, even though there's 10 adults on the street, we don't have all 10 data values. We only have 3 of them. So we divide by 3 instead. Okay, so I'll just tell us that Xavier's sample mean is $67,000. Okay, so the average salary of the 3 adults that he surveyed again is 67,000. Okay, so the next student, Yolanda, again, exact same street. So her answer, well, her true answer would be the same as Xavier's answer. She happens to also survey David and Frank. So those two data points are the same. But instead of talking to Ingrid, she talks to Bob, right? So her data is different than Xavier's. Okay, so let's find Yolanda's sample mean. So again, for her, the three data points are 40,000, 55,000, and 70,000. So we add those together. Sorry, plus. Okay, so this comes out to 55,000. Okay, and then the third student, again, doesn't have time to do all 10 adults, so he only picks 3 adults to ask. He talks to 3 completely new people, right? Neither Yolanda nor Xavier talk to the 3 adults, Adam, Carla, and Ginny. Okay, so let's calculate Zach's sample mean, right? These are the 3 data points he has. Okay, so again, I need to emphasize they were all surveying the same population. They were all trying to get the data for the average salary of the adults on the same street. So if they had all done the full data set, they all should have gotten the same answer. Okay, but their answers are actually very, very far apart, right? 55,000 versus 67,000 versus 83,000. Their sample means are very far apart from each other. Okay, and again, neither of them made a mathematical mistake, or none of them, but just due to the randomness of, again, Xavier seems like he talked to people who are making below average. Zach looks like he talked to mostly people who are pretty far above average, right? So that randomness in who they talk to leads to very different results. Okay, so why don't we write down a few things about what we saw here. We'll say even though the 3 samples, let's say sample mean, sorry. Even though they were drawn from the same data set, whenever you do a sample, whenever you don't have the full data, whenever you're using only part of the data, so due to the randomness of who was in each sample, the sample means greatly varied. Okay, again, the sample means we saw were pretty far apart, 55,000 versus 67,000 versus 83,000. Okay, so like who was closest? We don't know. We don't know if the true answer is around 83,000 or 67,000 or 55,000, or maybe it's lower than all 3 or above all 3. Okay, so we'll say without the full set of data, there is no way of knowing. And here's a phrase we'll be using throughout the rest of the unit. There's no way of knowing the true population mean. Yes, Rebecca? Okay, so if you had multiple, uh, well, you would still probably need to know the individual values, not just the means, because it would be important to know whether some of the data overlapped, like Xavier and Yolanda, or if the data was completely different. But yes, having more data would definitely let you make a stronger conclusion. But even if I talk to, let's say, 29 out of 30 people in a room, I still can't be completely confident of the true answer because maybe that one remaining person is really high above or really below the average. Okay. All right. So, uh, how do we deal with the fact that, again, we can never be completely certain about the answer? Let's go and turn to the second page. Okay, so as we saw from that previous example, because sample data can vary so much, instead of trying to predict the true population mean or true mean, we instead create what's called a confidence interval. Okay, so we've used the word interval before in math. So it's not a single value, it's a range of values. Okay, so, it's a lot easier to um, be close to the answer if instead of saying, I think the answer is exactly 10, you would say, I think the answer is somewhere between 5 and 15, right? So giving yourself a range of values allows you to make a more likely to be accurate statement. Okay, so now confidence intervals are a balancing act. Okay, so let's go back to Xavier. Again, Xavier got a sample mean of 67,000. Okay, so Xavier understands that his answer is probably not exactly correct because he only talked to 3 out of 10 people. Okay, so he wants to go, less than, he wants to go in both directions. He knows the true answer could be less than his number or it could be more than his number. Okay, now, so let's say he gives himself a really big range. He goes 30,000 less and 30,000 more than his number. Okay, so if he says the true answer is somewhere between 37,000 and 97,000, he's probably right? He gave himself a huge range to work with. But the downside is this information is not useful, right? This is such a huge range of values that it doesn't really tell us anything. Okay, now on the other hand, if he said, yeah, my answer is 67,000, it's really close to the right answer. The right answer is somewhere between 66,000 and 68,000. If he is right, then yes, this would be very specific information, right? These numbers are very close to each other, but there's a good chance he's not right because, again, one person can throw off the whole mean. Okay, so how do we balance this? How do we balance being likely to be correct with having a narrow enough range for the info to be useful? Because again, if I told you guys, oh, the average on the final will be somewhere between 0 and 4, that doesn't really help you, right? If I told you the average is between 2.4 and 2.6, then that would be much more meaningful. Okay, so the range that we generally use is what's called a 95% confidence level. So confidence has a specific meaning in statistics, right? It's not just like everyday language. Confidence has a mathematical meaning. Okay, so what that represents, a 95% confidence level. If we repeated this process of taking samples, and constructing confidence intervals. If we did that many times, 95% of them would contain the true population mean. Okay, so this is saying that, yeah, in very rare cases, I may talk to almost all people above average or almost all people below average, and that may mean that my interval does not contain the right answer. But the vast majority of the time, 95% of the time, my confidence interval will contain the true answer. Okay, so in order to understand this, we're gonna take a look at a little animation. So give me a second to switch my screens. Okay, so we have a normal distribution, right? That's what we've been working with. Okay, it won't let me zoom in, sorry. Okay, so normal distribution, right? Bell curve shape. And we're gonna do a sample of 5 values. Okay, so we don't know what this represents, it doesn't matter, right? But we know that, okay, this dashed line is the true average. So anything to the right is above average, anything to the left is below average. But again, we don't actually know the distribution, right? Because the whole point of this is we don't have the time to get every single point of data. So we're just gonna pick 5 samples at a time. Okay, and so what this program is going to do is it's going to pick 5 random points from somewhere along this curve. It's going to average them, and it's going to create a confidence interval. Okay, so if the numbers were closer together, the confidence interval will be narrow because when the numbers are all close to each other, you expect that the rest of the numbers will be close also. If the numbers are far apart, like if you have some numbers from here and some numbers from here, the confidence interval will be bigger. Okay, so again, we don't know the true mean, but our goal is for 95% of our confidence intervals to contain the true mean. Okay, so hopefully it'll make sense once I start showing. Okay, so again, you notice it's taking 5 dots at a time, and then it's averaging them, and it's shooting out those little bars to show the confidence interval. So you see, the vast majority of these confidence intervals do contain the true mean, right? But this one missed. This one was mostly to the left. Okay, so all these are containing the middle, that one barely. We'll wait until one misses again. So right now we're getting lucky, right? Everything is containing the middle, some wider than others. Okay, so eventually, like we'll get 4 points on the left or 4 points on the right, and then it'll miss. Okay, so yeah, this is actually going really well. There we go. Okay, so this one just barely missed the center, right? But we wouldn't know that because, again, the idea is you only have one line at a time. So yeah, most of the time we will contain the true answer. And again, the reason some are wider than others, right? So you see, like those points were all really close together. That's why it's really narrow. But those were far apart, which is why the interval is wider. Right. So yeah, the further apart your data is, the wider the confidence interval because you're less certain about the data. Okay, so you see right now overall from this sample, 96% of confidence intervals contained the mean, and now 3% missed it. Okay, so again, our goal is 95%. Okay, but yeah, hopefully you understand the concept. Again, you don't know the true value. You're just looking at 5 data points at a time. So most answers do contain the true mean. Okay. Okay, let me switch back. Okay, so now that we have seen sort of the way confidence intervals work, how do we construct them? Okay, so there's a mathematical formula here. So you may have seen this on your reference sheet, the one with the z-score table. So you don't need to, well, let me take a step back. So you're going to be given this formula exactly like you see it here, but you need to know what each of these things mean. Okay, I'm not going to tell you how to use it or what each part stands for. Okay, so again, you'll get what's here in red, but what I'm going to label now in blue, you need to know on your own. Okay, so we already talked about X bar. This is the sample mean. Okay. Plus minus symbol you've seen before, right? Like in the quadratic formula. It means you both add and subtract separately. This next thing, Z with like the asterisk after it, this is pronounced out loud as Z crit, sort of like the critical level. And this represents the Z-score corresponding to the desired confidence level. Okay, because if you want to be more confident that your interval contains the right answer, right? Like, for example, if my interval is, oh, I think the true answer is somewhere between 5 and 7. If I increase my interval from 4 to 8, then, okay, now, yes, I'm more likely to contain the right answer, but the range is now wider, right? So it's less meaningful information. Okay, so it's, again, always a balancing act. We've already talked about sigma. That is the standard deviation. Remember, that represents how spread out the data is. Right, so if in your sample the numbers are very far apart, that would be a large standard deviation. Okay, and then lastly here, so square root n is what's in the formula. N itself is the sample size. Okay, so that's however many data points you have, right? So it's like the number of people you surveyed or the number of objects you measured or whatever. Okay, and you might have heard the term margin of error before, especially with like polls, right? So you may have heard, oh, like this candidate has a 45% with a margin of error of 3%. That's the reasonable amount above or below that they could be off. Okay, so instead of writing it separately, I'm going to do it like this. Okay, so this part of the formula is the margin of error. Yes.
Some number plus or minus 3.
Yeah. Yeah, exactly. And we'll do some examples in a second, but yeah, you would start with your sample mean, and then from there you determine how far below and how far above it, that's the plus and the minus, that your confidence interval extends. Okay, so let's now talk about Z-crit. Okay, so for this class, we're always going to do a 95% confidence interval. So we need to know what z crit is equal to. Okay, so first, let's draw a little sketch to understand what we're looking for. So let's go ahead and draw our normal curve. Okay, so what's our goal? Our goal is to get the middle 95%. Okay, so not the left 95, not the right 95, the middle 95. Okay, so that means we need to cut it off on both the left and the right to be in the middle. All right, so our goal is to get the middle 95%. Okay, so now the problem is we know that our z-score table does not tell you in between. It only tells you all the way to the left. Okay, so let's figure out, okay, what's the area all the way to the left? Okay, so all the way to the left from here. Well, if this is the middle 95%, the remaining 5% has to be evenly split between these two tails. So, right, so again, the full curve is 100%. We've already used 95%, that leaves 5%. Split evenly because it's symmetrical. So divided by 2. Right, each of the two tails is 2.5%. Now, since the area to the left is this and this combined, you would add them together. Okay, so 95% plus 2.5% means we're going to use the table to look up an area of 0.975 to the left. Okay, so we're going backwards from normal. Normally, you know the z-score and you look up the area to the left. This time, we already know the desired area to the left, and we need to figure out the z-score. Okay, so again, this is not the z-score, this is the area. Okay, so looking at the table from last lesson. Okay, we want to find an area of 0.975. Okay, so again, not the z-score 0.9, but area 0.9. Okay, so where would that be? Right here. All right, so this is an area of 0.975 to the left, which is what we want. Okay, so what z-score leads to that area? 1.96. Okay, so let's write that down. Okay, so again, what did we just figure out? That a z-score of 1.96 gives us the 97.5% to the left, which means it'll also include the middle 95%. Okay, so our conclusion, z-crit will be 1.96 for a 95% confidence interval. Okay, so this is a number that you will need to have memorized. You're going to use it in tons of practice problems, so you'll probably begin to remember it without having to, specifically try. But Yeah, you're not going to be given this number, so you need to know it. Okay, so just so you're aware, some other places, they just round this to 2. They use zcrit as 2, but we will be using the more precise 1.96. Okay, so now we need to understand the relationship between sample mean, margin of error, and the confidence interval. Okay, so again, let's say that you had something like 5 plus or minus 3. So if you did 5 minus 3, that would be 2. On the other hand, if you did 5 plus 3, that would be 8. Right, so the confidence interval you would write as bracket 2 comma 8 bracket. We know from interval notation that this means that it can be anywhere between 2 and 8, including 2 and 8. Okay, so now to do it for more general terms, to construct a confidence interval, what you call the lower bound, so that's like the lowest possible number that is reasonable. You take the sample mean minus the margin of error. And then to find the upper bound, you instead do the sample mean plus the margin of error. Okay, and then the confidence interval itself would be bracket lower bound, comma upper bound. Okay, so just to do a specific example, let's say that you've already calculated that a certain sample set has a sample mean of 80 and a margin of error of 6. Okay, so the lower bound, from 80, you can go up to 6 below. So 80 minus 6 means you think 74 is the lowest reasonable answer. Upper bound, from your sample mean of 80, you also could go up to 6 above it. So 86 is the largest answer that you think is reasonable. Okay, so your confidence interval, which I'll abbreviate CI, would be bracket 74 comma 86 bracket. Okay, so now let's try doing a full problem. Okay, so let's say you're trying to figure out how many minutes the average adult spends watching television each weeknight. Hey, you're never going to be able to get the data from every single adult, right? There's literally millions in the US. Okay, so you do a sample. You do a sample of 400 adults, you collect their data, and the average time, the mean time of those 400 adults is 68.4 minutes. Okay, and you do a calculation to find the standard deviation of that data set is 20.9. Okay, what's a 95% confidence interval for the population mean? And whenever I say interpret its meaning, I mean give me a complete sentence that tells me the conclusion. Okay, so let's go through these things one by one, right? Our goal is to create a confidence interval. So we'll be using this formula. So we got to fill in all of these parts. Okay, so one thing at a time. What does the 400 represent? The 400 is how many data points you have. It's the number of adults that you surveyed. So N is the sample size. Okay, so n is 400. We'll come back to that. Of those 400 adults, the mean time was 68.4 minutes. Again, this is not the true mean. We have no way of getting that without all the data. This is what we call the sample mean. Okay, so the 68.4 is going to be x bar. Okay, make sure you put the bar on top of the x. With a standard deviation of 20.9 minutes. Okay, so standard deviation we represent with the Greek letter sigma. Okay, and then determine a 95% confidence interval. So like we said above, for a 95% confidence interval, we use z crit equals 1.96. Okay, so we have everything we need now. So we're going to substitute these into our formula above. Okay, so x bar is 68.4 plus or minus z crit, which is 1.96, and then times the fraction of sigma, which is 20.9, over the square root of n, which is 400. Okay, so you definitely need a calculator for this part. The numbers will almost always be decimals. Okay, so the good news is because you're going to do both plus and minus, you can just edit your first answer to quickly get the second. So let me show you what I would do for my calculator. Okay, so I would start with the sample mean, 68.4. I'll do the minus first. Oh, that's lagging a lot. Okay, there we go. Okay, so 68.4. Again, I'm going to do the minus first. Minus 1.96 times the fraction. So the numerator is 20.9, and then divided by the denominator, which is the square root of 400. Okay, so the minus answer, 66.3518. Okay, so let me write that down real fast. That's going to be my lower bound, right? Because the minus is the lower answer. Okay, and that'll be comma the upper bound. Okay, so for the upper bound, I don't need to retype the whole thing in. I just go back and edit. I change the minus to a plus because it's a plus minus symbol. Okay, so the upper bound would be 70.4482. Okay, so this is my confidence interval. Okay, but now we need to interpret the meaning because these numbers are not helpful if you don't understand what they represent. Okay, so here's the phrasing that we will use to describe the meaning of this. We'll say with 95% confidence. Yeah, again, you have to say that because otherwise, with 99% confidence, with 90% confidence, those confidence intervals would all be different. Okay, so again, we used a 95% confidence level. Okay, so with 95% confidence, the true population mean, or okay, so again, we have a sample mean, but that's not really what we care about. We're trying to come up with a confidence interval for what we call the true population mean. So that's the real answer. If we somehow got every single person's survey data, that would be the true answer. Okay, and then you also need to tell me what are these numbers measuring, right? Are we measuring oranges or miles or people or dollars, right? So for this problem, we're measuring minutes spent watching TV. Let's just say that. Well, TV each weeknight. Okay, and then you tell me it's between, and then you list the lower bound and the upper bound. So yeah, this would be an example of a complete interpretation of the data. Okay, so this is a relatively small range, right? It's only 4 minutes from the low end to the high end. So this is meaningful data, but 95% confidence is pretty good, right? We saw from the animation that 95% is a lot, right? 19 out of 20. So yeah, chances are the true answer is somewhere between these two numbers. All right, so go ahead and take a minute and see if you can construct a confidence interval for the second situation. And again, also write a sentence describing the findings. Okay, so I'll give you guys a few minutes to try that out. All right, so here we had a sample size of 224. The sample mean is 2.6. Standard deviation 0.7. And the Z crit for 95, it's still 95%, so it'll get again be 1.96. Okay, so 2.6 plus or minus 1.96 times the fraction 0.7 over the square root of 224. So I didn't tell you where to round to. So I'm just going to go to 4 digits here because that's how many I went to for the previous problem. If you rounded somewhere else, that's fine. Okay, now we want to be careful about the wording, right? Because what do these numbers represent, right? Is it like 2.5 people, $2.5? It's not 2.5 students, and it's not 2.5 athletic events either. It's that many athletic events per year that the student attended. Okay, so the sentence that I would give with 95% confidence, the population mean for, and again, this is talking about how many athletic events the student attended. Okay, so it's going to be between those numbers. Okay. So questions on anything on these first 2 pages? Okay, so let's continue on. Okay, so here are two different scenarios. Scenario A, basically, students are being asked, are you going to vote for this person for ASB president? Okay, the second question is you're asking the students, how many hours do you spend doing homework each night? Okay, so there's a key difference in the type of data that is collected. Okay, so you want to think about, you want to pretend that you are in the survey, they are asking you the question. And the main thing is your answer going to be a number or not? Okay, in the first scenario, right, if someone walks up to you and says, hey, are you going to vote for, you know, Bob for president? Your answer is either yes or no, right? Those are not numbers. On the other hand, over here, if someone asks you how many hours do you do homework a night, your answer is a number. Okay, so we treat these situations differently. Okay, so let's write that down. Okay, so in situation A, we say the data response is not numerical. On the other hand, in B, the data response is numerical. Okay, again, in A, your answer is going to be yes or no. In situation B, your response would be a number of hours. Okay, so looking back at the previous page for a moment, right? So this example, the question was, how much time do you spend watching TV? The answer is a number of minutes. Over here, the question is, how many athletic events do you attend per year? So the answer is a number of athletic events. Okay, so the previous formula is used when the data is numerical, right? That's what we call sample mean. Okay, but when the data is not numerical, you instead have what's called a sample proportion. Okay, so the formula that we have here, so again, sample proportion is used for data that is non-numerical. Right, because you can't have a standard deviation if the data is not a number, right? Like when the numbers are 5, 6, and 7, you can say the answers are close together. When the numbers are 1, 10, and 50, you can say the numbers are far apart, right? But what if I'm doing a survey about favorite colors, right? Like green and blue, are those close together or far apart? Are they farther apart than green and brown? You can't measure those because they're not numbers. Okay, so we need a different formula when the data is not numerical. Okay, and here is that formula. So P with a little like up or a caret or you say this, let me just write the formula first. Okay, so yeah, that P with a, yeah, it's kind of funny. P hat. So yeah, it looks like the letter P is wearing like a little like party hat, right? Um, And this represents the sample proportion. Okay, so a proportion is like a percentage, right? It's like what percent of respondents met your data. Okay, so again, when you ask people, are you voting for Bob for president? They either say yes or no, which are not numbers, but you can say, oh, 70% of people said yes. So you could use 70% as your sample proportion. Okay, and the rest of these we've seen before. Z crit is the same, and N is still the sample size. Okay, and then like before, the thing after the plus minus sign is what's called the margin of error. Because that's the amount you're allowed to add or subtract from your sample value. Okay, so we're gonna go back and now actually construct the confidence intervals for the two problems at the top of the page. Okay, so looking back at letter A, again, this is collecting non-numerical data. They're asking, are you voting for Bob, yes or no? So since the data is not a number, we use a sample proportion. So yeah, just always imagine yourself, what if you were being asked a survey question? Would your answer be a number or not? Here it is not. Okay, so now we need to go back and figure out the actual confidence interval. Okay, so 600 students were polled, so that's your N. And 57% said yes, they're voting for Bob. Okay, so we do want to convert this to decimal form, not percent form. But yeah, this is your p hat. This is the sample value. Okay, so 57% in decimal form would be 0.57. And again, we are using a 95% confidence level, which means that Z crit is 1.96. Okay, and that's all we need, right? Those are the only three variables in the formula. Of course, one is a constant. And you notice p hat shows up 3 times, but it's going to be the same every time. Okay, so what we would type into our calculators, we've got 0.57 plus or minus 1.96 times the square root of 0.57 times 1 minus 0.57. And all of that is over N, which is 600. Okay, make sure you see that N is still inside the square root. So make sure you type it in so that N is getting square rooted also. Okay, so again, for me, I will do the minus first. Okay, 0.57 minus 1.96 times the square root. So the numerator, 0.57 times, so parentheses, 1 minus 0.57. Close parentheses. And that's divided by the sample size of 600. And then I'll close up the square root. Okay, so the lower bound would be that number. And then the upper bound, instead of minus, you just edit it to a plus to get that. Okay, so again, I'll just go to 4 decimal places for now. Okay, so I get 0.5304, comma 0.6096. But we could also convert this to percent form because that's usually a little bit easier to understand. So moving the decimal point twice, right, 53.04, and then now you need the percent sign, 60.96%. Okay, so based on our sample data, we think it's very, very likely that student A will win the election because we think that their true percentage of votes received is somewhere between 53% and 60%. It's very, very unlikely, right, that the true mean is below 50%, which is what you need to have the majority. Okay, of course, it's possible, but unlikely. Okay, so what this represents with 95% confidence. Okay, so you could say the true population proportion. I'll just say true percentage. Okay, and again, what are we measuring? We're measuring if students voted for student A. Okay, so this is the true percentage of students who voted for student A. Okay, so we think that that true percentage is somewhere between 53.04% and 60.96%. Okay, and then how about the other problem? So here, again, the data is about how many hours do students spend doing homework each night. So if you were part of this survey, your answer would be some number, right? Maybe it's 1 hour, 2 hours, half an hour, but it's a number. Okay, so for part B, the survey response is numerical. Sorry, is with an S. Okay, so this time you use the sample mean. Okay, so now we're back to the formula from the front page. Okay, we have the sample size, we have the sample mean, we have the standard deviation, and because it's 95%, the crit is still 1.96. Okay, so here would be your formula. Okay, and then doing the minus to get the lower bound and then the plus to get the upper bound, we should come up with 1.42, technically 4280, but I'll just leave off the 0. Okay, so that would be your confidence interval. And then what this would be written as a sentence. Okay, so let's remember, what do these numbers represent? You got to go back to the problem. Okay, we're trying to measure how many hours they spend doing homework each night. Okay, so these numbers are hours spent doing homework each night. Okay, and then it's between the lower bound of 1.428 and the upper bound of 1.572. Okay. All right, so once you have that down, I'd like you to take a few minutes and try to work through the mixed problems below. Okay, if you finish the first two, you can continue on to the next page.